theory today. We're going to look at pictures and some videos and talk about phase transitions. And one of the things that I've emphasized the last few weeks about phase transitions is that not all phase transitions are the same, but at the same time, they're all the same. Right? There's two different, we're going to see that there's two different fundamental classes of phase transitions. And I want to talk about the differences between them using the tools we've constructed, and then look at examples and try to understand the fundamental differences between the two types of phase transitions. And so I'll start today talking about the kind of phase transitions that we're comfortable with, freezing, boiling. And we'll look at how thermodynamics functions across these boundaries as we go from delta G changes signs from positive to negative for some phase process. And what we came up with over the last few lectures was that pure materials tend to develop these phase diagrams that tell you as a function of temperature and pressure what is the dominant phase, and they all kind of have the same structure, right? So they all kind of look like this, right? This is a classic phase diagram of anything. Okay, it doesn't really matter what it is. This could be benzene, it could be carbon dioxide, any sort of material. This is what it's going to look like, right? What is going to vary. Right? So in general, the topology, if you will, the general structure of the phase diagram is universal, right? So for chemical materials, the shape, if you will, the general shape of the diagram is effectively universal. But the things that's dependent on materials, right? Material dependent quantities well, they include the different special points on the curve, right? We have a couple of special points here, right? One of them being the triple point, right? Which is this point right here. I'll call the 3P, the triple point, right? And of course, at the triple point, the definition of the triple point is that the Gibbs energy of the gas is equal to the Gibbs energy of the liquid, which is equal to the Gibbs energy of the solid, right? So they're all the same energy there. All three phases are at equilibrium. So every material has a triple point. In fact, I'm going to skip discussing this. It's kind of an old, antiquated concept, but Gibbs himself proved that every pure material has exactly one triple point. Wow, okay. Yeah, say a pure material. There's also the critical point, right? The critical point. Which is, of course, where the vaporization enthalpy is equal to the change of the entropy change of vaporization, which is equal to 0, right? Where the liquid and the gas become identical. Right? And the rest of it, right? The only other thing that is something material dependent, of course, are the slopes. The other one is, of course, the slope dp/dt of these curves, which as we derived is delta S over T delta V. Right, so the slopes of these curves, of course, depend on the entropy changes, the volume changes, right, the densities. So of course they're slightly material different, right? They're going to be different for water, right? Because water, when you freeze water, you lose density. So the slope is opposite what it is for any other solid, right? Benzene, CO2, basically every solid except for water becomes more dense. The delta V is a given sign, but in ice, it's the opposite. Okay, so there's basically just three kind of quantities that are material dependent, but everything looks the same. It all kind of looks like this. And the thing I want to really focus on, there's not really much else for us to really probe here. Because all gases are the same, all liquids are the same, all solids are, well, I'm gonna say that the same. But liquids and gases are all the same. We can talk about this transition between liquids and gases and fluids. For fluids, all we want, not really all that much different. But the solids are very interesting. Because we saw that again, this curve, the thing that connects between liquid and gas, that disappears at some point. So again, liquids are ephemeral. They only exist in a certain set of qualities, only a certain set of conditions. Liquids are special. Liquids and gas eventually converge, and then there's no distinction between the two anymore. But solids, we don't have that luxury, right? We saw, I argued to you last class that the enthalpy change from a liquid or a gas to a solid is not equal to zero, regardless of the temperature or the pressure you're at. There is no critical point for solids because solids have a different symmetry, right? They're anisotropic. They don't have the isotropy where everything looks exactly the same at all locations that a liquid and gas does. So this line, the solid line, continues on for infinity. Right? It might level out, it might increase, right? It might go up. Who knows, right? The solid line, the solidus line, as we call it, always exists. And I want to drive that point home today. So where the interesting parts about the phase diagram, really, in terms of the phases of matter, is really the solid phase. There's two interesting points. There's this critical phase out here where the liquid and gas are the same. I think that's kind of exotic and unique. But the solids in particular are where uniqueness is shown. Because the thing is that there's really, in some sense, there's only two ways or one way to make your material isotropic, where it's the same everywhere. That's just a fluid. And there's either two fluid phases or one fluid phase. There's only one way to do it in some sense. But in solids, there's many ways to organize atoms or molecules together into a stable orientation that's fixed in place, like a solid. There's crystalline forms, right? I mean, just think about carbon, for instance, right? You guys know versus graphite, which you buy which is in your pencils. There's also diamond, which some of you may own, some of you may not, some of you may own eventually. Very, very distinctly different structure, different properties than graphite. There's also buckyball, C60. That's a solid form of carbon. Buckyball, C60. Buckminster fullerenes. I'll show you a picture of one if you've never seen it. I don't know if you guys have, you can't see that. I'm sorry, right? Right, this is another what we call an allotrope. It's a different phase of solid carbon. There's graphene, graphite. There's all sorts of different ways to stably orient carbon atoms together in a solid. The buckyball is just a powder of these little balls of 60 carbon atoms. But that's very different than graphite. Graphite are long planar sheet. So there's lots of different ways to do it. And what I want to focus on in particular, just to highlight this, is the most interesting and most complicated and most ubiquitous molecule in the universe on Earth is water. Ironically, water is something that we all have to live with. We have to study, we have to understand, because of course we are majority water. We live in a majority water place. I don't have to explain to you why water is important. But unfortunately, when it comes to solvents, when it comes to molecules, water is one of the most complicated to understand. So it's a little unfortunate for us as training scientists, young scientists, that the most important chemical is also the hardest to understand. And there are people who spend their entire lives studying water, and I want to highlight some of that work. So the question I have is what does the world of solid water look like? What does ice look like? Is it really just the ice you know? And in fact, that's not the case. The ice that we know is just a small section, the entire solid phase diagram of water. In fact, water has something around 19 or 20 different solid phases. And I want to show you the phase diagram of water that is more up to date. And you'll see that this is a subset of that phase diagram. see all of these features, but only in a very, very small region of phase space, of parameter space. At other temperatures and other pressures, it's going to be much more complex. So here's a picture of the phase diagram for water. So let me orient you a little bit. Let me copy this over so I can draw on it for you. That's probably a good idea. Okay, sorry about that. All right, so this is the phase diagram of water over everywhere from absolute 0 to about 700 Kelvin, and a range of pressures all the way down to 10 microbar, which is effectively high vacuum. It's about, 100,000 times less than the atmosphere, all the way to 10 million times an atmosphere. So a very, very big phase diagram. Right, and the region that we just looked at on the previous slide, the traditional phase diagram, is just this right here. Right, this right here is the triple point. Here's the critical point. Right, so here's the liquid gas line running from here to here. Here's the boiling point of water. And this is where we melt. Right, this is 1 atmosphere and 0 Celsius. This is where water freezes. Right, so this is the area of water that we know here on Earth, the one that we are used to. It's just this small section, but if I go up, right, or go to the left, cool down, or go to high pressure, you can see things get much more complicated. And so as I move away from, let's say this is water ice, this is what we call hexagonal ice, which is the ice that's six-folded, six-sided snowflakes. So it's hexagonal ice. We go up, we see that there are, at, of course, very, very high pressures. This is, 10,000 times atmospheric pressure at 10 kilobar. There are multiple phase transitions into other solid forms of water. Right? So different crystalline structures of ice. And the region that we live in, right here, is what we call the I/H category. This is what's called hexagonal ice. And that's where we live. And you can see that if we were, in some sense, if we were actually colder, if the world was a colder place than it is, we would actually be in this ice of sea region, which is a different form of ice called cubic ice. All right, let's look at what those look like. Okay, maybe there's something we can learn and correlate between the structures of these crystals and the conditions at which they exist. So let me just show you a crystal structure, kind of a cartoon. I'm going to come back to this slide of hexagonal ice. Right, this is called ice sub IH. This is what we know and love. And if you look very closely, you can see why it's called hexagonal ice. Right, it has the unit cell. This is a unit cell of water. So one ice crystal, single water ice crystal, a single crystal looks like this. Okay. And you can see that if I were to draw a little diagram here, right, where this has six-fold symmetry, right? It's got that six-fold hexagonal symmetry. Right? This leads, of course, to, right, this leads to our six-sided snowflakes. Right? But this is only stable at a small set of conditions. As long as T is within 5 and 273 Kelvin, then the pressures are anywhere between 1 and 2,000 atmospheres. All right, so that's actually a pretty big range, right? It's very stable. Water loves being in this arrangement. It's actually a very, very stable arrangement. That's why it's so common. And what you actually find is that each, that's supposed to be an arrow, each H2O molecule is hydrogen bonded to 4 others in a tetrahedral arrangement. So you can kind of imagine if you look at each of these waters, they're kind of arranged in such a way relative to the other waters that it kind of looks like methane. You have a water in the middle, and then you have a water pointing straight up, and then an angle of 109.5 degrees. And in tetrahedral geometry, you have other waters. So this is like, in some sense, like a perfect structure. Something that you learn in chemistry is that chemistry loves high symmetry. They love to be, stable things tend to be very highly symmetric. And so you have two really great symmetries here. One, we have an overall six-fold symmetric symmetry, right? Remember, cyclohexane in particular is one of the more stable cyclic hydrocarbons. It likes being six members, likes to be a six-sided ring. So you get that six-fold symmetry here, but also each element also has tetrahedral symmetry. And of course, we know that tetrahedrons are really good in chemistry. So hexagonal ice is like, in some sense, a beautiful and perfect crystal. It has everything going for it. But it's only stable at certain regions. And so at low temperature and low pressure, I think about like at the top of the atmospheres. So upper atmosphere. And also this, you see this in the Jovian moons and planets. Right, so Jupiter, Saturn, and so on. You see that water actually forms a different structure. Sorry. What we call cubic ice. Right, and so what's different here? Well, each water, it doesn't show the hydrogens here, right? Each water sees four other waters, so the tetrahedral arrangement. Oh, no, sorry, it only sees three. Right, so now only each one sees three. Oh, sorry, yeah. So this is now not tetrahedral, it's trigonal planar, or trigonal pyramidal. Right, each water sees another three. Right, and it also, over the overall symmetry, is fourfold. Right, so we have a square, or what we call cubic symmetry, right? So these snowflakes, so the snowflakes on the Jovian moon, well, I should really say the ice crystals. It's not really snow, but the ice crystals in the upper atmospheres of Saturn and some of the colder moons that have water, they form cubic ice. So they have square snowflakes. Right. So you might want to ask, like, here's an interesting question, right? So let's go back for a phase diagram and understand that while we have hexagonal ice here, that's what we can create in the lab. So why can't I just take hexagonal ice? I want to make cubic ice. Like, cool idea. I'm doing that. I'm gonna just take hexagonal ice and cool it. I put it in liquid nitrogen. I imagine I take ice right here, and I drive it down to here. Liquid nitrogen, I'll just write it here, is about, that's 100 Kelvin, 80 Kelvin, 70, so it's about right here. This is liquid nitrogen. Right, so I could drive it towards liquid nitrogen, right? So what would I expect, right? I would take my hexagonal ice and I would drop it down to 77 Kelvin. As I cross this line right here, this is the line of delta G equals 0. So as I cross this line, cubic ice now becomes spontaneously favorable, delta G is negative. So I'd expect it to convert to cubic ice, but it doesn't. I pull it out and all I get is extra cold, extra frozen hexagonal ice. Now, why is that? I just went across the barrier. Delta G is negative. It should be spontaneous for me to convert to cubic ice, but it never happens. And why is that? Well, the understanding is that, yes, technically cubic ice is more stable at these conditions, but let's think about the actual physical process to take hexagonal ice and make cubic ice. So what I have to do as this hexagonal ice is cooling, I'm pulling heat out of it. And so it's losing energy to do stuff. This is becoming more stable. The cubic form is becoming more stable. But in order to take this and to do this, convert it to this, right? I have to take each of those molecules, right? They have to lose one of their interactions. Right here, each water sees 4 other waters. I'll draw it for you. So there's 1, there's 2, there's 3, and there's 1 behind it, 4. So this sees 4 waters. Each water sees 4 hydrogen bonds. We have to put it into a different arrangement where there's only 3 hydrogen bonds. So you're losing 1 hydrogen bond per atom per cell, or per molecule per cell. And we have to rearrange the entire lattice from 6-fold symmetric to 4-fold symmetric. So there's 2 changes, right? There's a chemical change. We have to change the bonding characteristics of the molecule and the crystal. And then we have to do PV work. Right? So this requires a change in chemical enthalpy, chemical heat, and also PV work to facilitate this change. How the hell is anything going to get that done as you're slowly sucking heat out of it? Right? So the idea, of course, is that if Gibbs is negative, that means that the entropy change, or the enthalpy change of the system is balancing out, that there's enough energy in the system to facilitate that interaction. But the problem about this process is to get to the final point, to go from here as a beginning point to the end point, we have to break a bunch of stuff. So the energy is going to have to skyrocket as we break stuff, and it's going to, everything's going to move around at some high energy. And then eventually it'll find itself in the cubic, right? But the system needs to have that energy to rearrange in the first place. And that's not indicative, that's not accounted for in Gibbs free energy. Gibbs free energy only considers the difference between the products and the reactants, or vice versa. Anything that happens in between is immaterial, but of course it matters, right? That's what kinetics is. Kinetics says that there is you have to put energy into this to break it in order to form something new. And you get some energy back when you form the new thing, but it still takes energy to what we call an energetic barrier to get it started. And so when you go through this process, taking hexagonal ice and cooling to cubic, nothing happens. It just doesn't have enough energy, input energy, to overcome that barrier of rearrangement. So how do we get cubic ice? Well, the way that people typically get cubic ice is they go away, they go out. So what they would do instead, it would be, for instance, the start at 0 degrees, right? And then melt it. Let me do a better color than that. Sorry, let's do yellow, right? Instead, to melt it, to pressurize the liquid, because of course it's very hard to pressurize ice, much easier to pressurize a liquid. And then supercool it very, very rapidly to this temperature. All right, so the idea would be to warm it up, give it some heat, pressurize it, and then rapidly cool it. So it just skips over the hexagonal ice. It never has a chance to freeze into the hexagonal form. So what we have here instead, initially, what we would have is just some super cooled liquid, right? Be super cool. Let's see what that actually looks like. So you can actually do this with, if you've ever been to like Six Flags, you got this, I don't know if they still do them anymore, but Coke used to have these machines where you pay like $4 for 20 ounce. It ripped off and it's really, really cold. And then when you open it, it immediately becomes a slush. And what that is a refrigerator that keeps the Coke sealed and pressurized, of course, because it's in a 20 ounce bottle, but it keeps it below freezing point. So when you open it, it causes the stuff to freeze out. And this is what that is. So it's a supercooling process is. And the idea here, this is just creating hexagonal ice. Maybe you've seen this before, maybe you haven't. This is just Fiji water that's just put in a freezer and cooled, right? And it's just a liquid. And then when he opens it and shakes it a little bit, right, or he whacks it, right? it starts to spontaneously freeze. So that's 10 Fahrenheit, right? So it's 20 degrees below the freezing point of water, but it doesn't freeze until something happens, right? A mechanical shock causes it to freeze. This is exactly how we would create cubic ice, right? We would take water, pressurize it, then supercool it, and then give it a knot to freeze in the cubic ice. The problem is that once you're in an ice section, once you're here in hexagonal form, it's very, very hard without melting to break that ice. You just don't have enough energy. So instead, what we do is we go out of the way and take a scenic route by pumping in some heat and then supercool. And this idea of supercooling is really, really important because what we've done, what we have in that video, what he's effectively done in that video is he's driven this liquid water very, very quickly to some very cold temperature below the freezing point, right? So if he was at like 10 Celsius, minus 10 Fahrenheit, which is probably about right here, just past the freezing point. And the water hasn't frozen yet, right? Why not? Well, the thing is that in order for something to freeze, the ice needs to nucleate, right? You need to have this nucleation event where the water begins to freeze on some surface or some little piece of dirt or something like that. So if you have very, very clean water and a really, really clean bottle that doesn't have a lot of microabrasions on the inside, there is in some sense no surface in which the water can nucleate and freeze. Right? Remember that freezing doesn't happen simultaneously. Spontaneously, it happens locally at some point, and then the crystal grows. It nucleates out. And if there's nothing to nucleate at, then the barrier to begin crystallizing the water is so significant that the water doesn't nucleate. It doesn't freeze. It just stays liquid. Even though delta G, right? Delta G says that we should have ice. But the problem is that we haven't provided a condition in which it becomes energetically favorable for that transition to occur. The kinetics are not favorable. And so we have to put in some sort of nucleation event in order for the water to freeze spontaneously. And of course, the way he did that was to hit the bottle, shake the water up, give it some mechanical energy in order to allow the rearrangement and nucleation. He's mixing it up and stirring it up and making it a little chaotic to hopefully get a nucleation event. Yeah. And the driving home point of that, and again, this is the same thing on the other side as well. When we boil, the same thing can happen as well, right? You can superheat a liquid and it won't boil if it's properly clean. I have another video of that. Right? You could do this with your microwave. I've done this before by accident. You have a really nice glass container that you heat water up in, and you heat it up and you pull it out and it just looks like water. You're like, it's got to be boiling at this point. And it doesn't. It's just sitting there, and then you put something in it. Right, you create a nucleation point for the phase transition, and the whole thing spontaneously boils. This is very easy to do in a microwave. Not that hard. You just have to have clean glassware and decent water. New Haven does not have decent water. But if you buy like distilled water, it's very easy to distill water. Right, and so the point is that, and I want to drive this point home, is that these phase transitions, first order phase transitions, they're local events. Right? They don't occur spontaneously energetically, but the reorganization energy, the amount of energy you need to put in to get it going is significant. And so you need to have some event, local event in your mixture that kind of catalyzes the product thing. And so first, once it gets catalyzed, then there's like this feedback loop and the whole thing goes. Just like the important thing is that in these events, they all happen locally. Like you have to have that nucleation. Now, in boiling, you recognize this nucleation event as bubble formation. Right? What happens is you vaporize some of the water and it forms a little bubble, and then it pops and it vaporizes, and the process continues. So bubble formation is also a nucleation event for gases. So it's just like freezing has nucleation. So that's the important thing. First order phase transitions happen locally. They happen gradually, and they require like a jiggle, right? They may require some kick to get started until you really pull enough energy out. Well, we should watch The Truman Show. That's be a good one. You guys ever seen that? That's a good movie. So I just wanted to make a note there. I found this this slide on Wikipedia, I was just thinking about nucleation. And this is some data of very, very small water droplets. I think they're about 300 microns in diameter. And this is the survival probability of the liquid droplets as a function of temperature. So what the survival probability is, does it freeze or not? Okay, so these droplets are about 350 microns. They're really, really small micro droplets of water. And you can set them to different temperatures. These are pure water, distilled water. And you can see that even at minus 20 Celsius, these droplets, they don't freeze. Right? Because they're very small and they require a nucleation event. The entropy change is not significant enough to really drive the freezing process. It needs a nucleation. And so if you create these droplets that are particularly clean, even at minus 20 Celsius, 20 degrees below the freezing point, they don't freeze. Right? It's not until you get about minus 30 that it takes that. Now the equilibrium is driven completely towards ice, and they nucleate spontaneously. So even though, and this is true again on the other side for boiling, the exact same process happens on the boiling side for hot things. Liquid water droplets of small amounts, if they're heated to above 100 C, have some survival probability that they won't spontaneously fall apart into vapor. It has to do, of course, with the surface tension of the material. It has to do with all sorts of different problems. Okay. So that's the really big thing about first order phase transitions, that they're local. They happen gradually in nucleation events. But there's another class, phase transitions. And I want to think about those for the rest. And what I want to first do is compare our two types of phase transitions. So we're looking at melting and freezing and so on. And I want to compare it to the critical point, which I claimed is a different type of phase transition altogether. And so let's look at these two different phase transitions from the point of view of some of the numbers that are some of the things that we've looked at in class. So what I have here is a really nice diagram that I stole from the internet a couple years ago of different parameters that we've considered or we've talked about and how they vary in their behaviors between a first and second order phase transition. So this, for instance, this would be vaporization or melting. Notice that the x-axis is an increasing temperature, and this is the critical point. We'll see that there are other things that are similar to this as well. And let's look a little bit, let's just kind of walk through this and see if we can just, rationalize each of these points. Of course, the first one, of course, is molar volume, which I should say is one over the molar density, right? Moles per liter. And of course, what happens is that when you boil or melt, that density changes, right? You have to say, for instance, the density of the liquid here. And the liquid is dense. And then you have the gas here, right? And at the boiling point, this is the boiling point right here, phase transition point, you have a discontinuity, right? Because you go from a dense material to a gas, which has a much higher density, or much lower density, or much higher molar volume. So there's a discontinuity in the volume. I'll kind of just draw it here, right? Where the volume, as you go across that phase transition, just magically jumps. It's not continuous. Right? Again, enthalpy, you guys have been working on that. Of course, boiling and melting has an enthalpy change. That's what you're calculating. Enthalpy of vaporization and so on. Right? This is delta VAP of H, for instance. Let me draw that a little cleaner. Right, and of course, we could do that with entropy as well. Right, entropy, it makes sense. Gases have a much higher entropy than liquids, and they, at the phase transition, they are discontinuous. There's a discontinuity. Jumps from one value to another. We'll come back to the second row, and we'll skip chemical potential now. That'll be our next. Actually, that'll be next week. Now, what about the heat capacity? Well, remember what the heat capacity is defined by. The derivative of the enthalpy with respect to temperature at constant pressure. So this is just the derivative of enthalpy. Okay, so let's look at that, right? The derivative is just the slope. So at every point up to the boiling point, or whatever point this is, the slope is basically fixed. Okay? We know that they slightly curve a bit. I'm looking at that from the homework, right? There's a slight curvature here, right? And so the heat capacity along this region of the diagram should just be basically a flat line at some value. Flat line at some value. It's got a little bit of curve, of course, because the heat capacity changes as a function of temperature. And then the heat capacity for the gas is also a flat line, and it should be a lower value than the liquid, right? Gases have less heat capacity than liquids do, so it's a lower value, right? But what about the value of the heat capacity at the transition? Well, let's think about the definition of the derivative. The definition of the derivative is the change in y divided by the change in x over an infinitesimally small change. So if we move across the barrier from this side to this side, right, we come in at some value and we come out at a different value. So if the difference in x between this point and this point is 0, or very close to 0, an infinitesimally small change from the liquid to the gas, right? That goes to 0 as the step size gets smaller, but the change in y is very large. The change in y is whatever the enthalpy of vaporization is. And so the derivative, as you approach the transition point, diverges because the denominator, the rise over the run part goes to 0, and the rise part continues to be positive. So that means that the slope of this line right here, as you get closer and closer and closer to the phase transition, diverges, goes to infinity. And that's exactly what it does. So the heat capacity starts here. And then what happens is the heat capacity goes to infinity. And then as you smoothly drive across to the other side of the phase transition, it goes back to the other value. Right? We've talked about this before. An infinite heat capacity means that it takes infinite energy to raise the temperature by 1 degree. And we know that when a liquid boils, it doesn't heat anymore. It just uses all of that input energy for boiling. So what happens is the heat capacity, therefore, is infinite at the boiling point, because any heat you put into the system is not used to heat the material. It's used to drive the boiling. So all this means is that external heating ceases at the boiling point, right? Only used to drive the phase transition, which of course requires a discrete change in enthalpy. So this is really nice, right? We can go put a calorimeter on material, and we can monitor as a function of temperature these different properties of our material, and we can learn something about its phase transition. Now let's look at the second order transition, the critical one. As you can see, the behavior is different. Volume, enthalpy, entropy, they're not discontinuous anymore. They don't have this continuity, right? But they meet at the same point, right? And of course that makes sense, because remember at the critical point, delta H is equal to 0, and delta S is equal to 0. So that means that the enthalpy on the right side is the same as the enthalpy on the left side. Okay? So they have to meet at the same point. Right? This is the critical point. Right? And we know at this point, delta H is equal to 0. So they have to meet. Same with the entropy. Delta S is equal to 0 at the critical point. So they have to meet at the same point. The entropy doesn't change as you move across that boundary. Okay? The volumes also do the same as well. Now, if we remember from last class, we can justify that, right, by remembering that the derivative of Gibbs free energy with respect to pressure at constant temperature is equal to the molar volume. All right. And so that means that if delta G is equal to 0 at the critical point, and delta H is equal to 0, then that means that the V of the liquid, and this is the fluid phase, the supercritical fluid, the V of the liquid is equal to the V of the gas, which is equal to V to the fluid, the supercritical fluid on the other side. So they're all the same value, right? That's the whole point of the supercritical, the critical transition, is that all the properties of the gas and the liquid converge. Let me draw it on the side of the board. Actually, let me finish up this argument. So the last thing we have to look at, all right, so these all make sense, right? Everything converges at that point, so that all the curves should meet at the critical point, or the phase transition. But this one's a little different, the heat capacity. Right, and you can see that the heat capacity is discontinuous there. Right, so it doesn't diverge, but the heat capacity has a discontinuity. Right, so slightly different than above, but this behavior looks a lot like this behavior. Right, so the things that are continuous in the second order phase transition are not continuous in the first. And the things that diverge in the first are discontinuous in the second. Now, what that means is, right, so what we have here is that the heat capacity, which is a derivative of enthalpy, diverges at the transition. And here now, heat capacity has a discontinuity, just like enthalpy does. So what that would mean is that the derivative of the heat capacity diverges for this system. So what this means is that the derivative of the heat capacity with respect to temperature at constant pressure goes to infinity. And what this also means, therefore, is that the second derivative of Gibbs energy with respect to temperature at constant pressure goes to infinity. So the big difference is, and here, so this is also proportional to the first derivative of the Gibbs energy with respect to temperature. So in a first order phase transition, the derivatives of the free energy diverge. So here, first derivatives diverge. And here, second derivatives. And in the second order phase transition, second derivatives diverge. Okay, so that's the key difference between the two, is that the things that are proportional to the change, right, things that are proportional to the change in the energy of the heat with respect to the independent parameters diverge at the critical, at the transition point. That's a first order phase transition. Things like heat capacity. But in a second order phase transition, those things, right, the energies and so on are continuous. But the first order phase transitions experience a discontinuity, just like the zeroth order terms do in the first order phase transition. And so the derivatives of this diverge. So the second derivative of the energy diverge. So what does this mean? Well, all it means is just this. Empirically, this is exactly what it means. It means that in a first order phase transition, there has to be a latent change in energy and latent heat absorbed or emitted. H has to jump. There has to be a distinguishing energy between the two states you're transitioning between. Your first order transition always has that. The fact that the first derivative diverges implies that the zeroth order function, which is the enthalpy, has a discontinuity. It magically jumps from one value to another instantaneously. That means an infinite derivative. Whereas a second order phase transition moves through energetically, smoothly through this boundary. But the things that are second derivatives of it, which tell you in some sense how fast or how slow the system will move in energy as you change the parameters, it's the acceleration, that diverges. What does this mean? And so let me show you a really cool example of this diverging second derivative, right? Because it's kind of hard to visualize what a second derivative is. I often think about it as the curvature as the function. Curvature. Something that has a divergent curvature means that a function magically changes from one curvature to another. And you can see that here in these drawings. You have this curvature that looks like this. And then you can see after this, you have a cusp, the transition point, and then you have a different curvature, a different acceleration. That would love physicists. Here you see it here, right? We have curvature here, and then it's a straight line. This has no curvature, and this has some curvature. That means the second derivative is changing at that point. There's discontinuity in that derivative. So let me show you an example of this. I've drawn this before for you guys. We draw the density around the critical point of a liquid and gas coexistence. This would be CO2, for instance. What we see is that there's some density that the system meets at, right? Remember, at the critical point, the density of the gas and the liquid are the same. So as we cool away from that, they should split because it becomes two phases. So as we cool away, one thing becomes more dense, right? This would be the liquid. And as we cool away this way, the gas becomes less dense. Right? So at the critical point, these densities meet. The critical density is the same as the gas, it's just the same as the liquid. Right? That's the critical point. And of course, here we have two phases, and here we have just one phase. Okay. All right, so let's think a little bit about derivatives and things like that. Right? So one thing that you can think about is the derivative of the density as a function of temperature. How much does the density change as we change temperature? And so I could just pick a point, for instance, on this curve, right, and calculate a slope here. Right? The derivative of the density with respect to temperature at constant pressure, right? And that's just some value, right? Here it's less than 0, which means that the liquid is becoming less dense as we approach. Of course, this means that the gas is becoming more dense as we approach. Okay, and what happens to these derivatives as we approach the critical point? Well, they become sharper and sharper. Right? Become sharper and sharper until we hit the point right in the center. Right? What's the derivative there? The derivative is straight up and down. Right, so at the critical point, at critical temperature, the derivative of the density with respect to temperature at constant pressure is infinity. It diverges. So what does that mean? Well, physically, what that means is that if I move the temperature, if I fluctuate the temperature a lot, the density of the material will fluctuate wildly. Right? It just means that the density has infinite variability with the temperature. A minuscule amount of temperature change evokes a dramatic change in the density. Right? So you can imagine if I have some material, I'll go back to a video. Some material that's at the critical point, and I've got some temperature distribution, right? Because not all you can't have the same temperature everywhere. It has to. When the top is cooler than the bottom, that means that the top and the bottom of that material at this temperature, if it fluctuates, it's going to have different densities at different regions. And even if the temperature fluctuates a lot, the density fluctuates, a temperature fluctuates little, the density fluctuates a lot because the derivative is very high there. Now, how does this connect back to the second derivatives that we had? Well, remember that we just calculated in the previous class that the derivative of Gibbs energy with respect to pressure at constant temperature is the molar volume, right? Which is equal to 1 over the density. Right? And we're interested in the derivative of density. And so that means then that the derivative of density with respect to temperature, that's me. Oh my goodness, what do we got? Is that a Kalea in there? Come in. Holy shit. Hi, what the fuck is this? Oh, my. Oh, you really went out of your way.
Oh, yeah. I always broke them. It's okay. I'll put it back down. Okay. Yeah.
Very good.
Just wanted to say
I'm very overwhelmed right now. Hi. Yeah, I bet you are.
I'm really sweaty.
Well, I was going to say, at least get some ventilation like last year.
Oh, yes. Okay, Larry. Thank you.
Okay, bye, Dino.
Bye.
Might get smacked by it.
Oh, yeah.
That was fun. Okay. Anyway, back to our discussion. So the first derivative of Gibbs energy with respect to pressure is volume, which is the proportional to density, 1 over density. And so if we take the derivative of density with respect to temperature, it's not too hard to calculate that this is equal to 1 over V times the second derivative of Gibbs energy with respect to with respect to pressure times respect to temperature. It's a second derivative of Gibbs energy. So density is a second derivative of the energy. And what did I say on the previous slide? That in a second order phase transition, the second derivative of the energy diverge. And that's exactly what happens. So this goes to infinity as t approaches Tc. Okay. So this is the key difference phenomenologically between a first and a second order phase transition. Is that the energy, in terms of energy, the phase transition is completely drama free. You're going from one state of the exact same energy into another state of the exact same energy. But what's happening is that the curvature, basically what you're doing is you're on one hilly surface of energy and you've transitioned onto a different hilly surface of energy that has the same energy, but a slightly different shape. So I can kind of think of it like this. This is kind of a weird way to think about it. A second order phase transition. If you imagine that you have some parameters, let's say P and T, and you look at the Gibbs energy of the system, you've got some curvature here, and here's the critical point. This is your critical point at this point right here. And, this is maybe liquid and this is solid or something like that. I don't know. Right. And what this means is that, and so this is your two-phase system. So this is 2 phases. What it means is that there's another curve of hills and energies and wells and orientations that is identical and right next to it in energy. So if I were to draw a little line, there's another coordinate where this point is mimicked at the same energy, and the curve looks completely different. So you can kind of think of this as the energy surface of a two-phase system. And this is the energy surface of a one-phase system. And at the critical point, the energy difference between the two surfaces is zero. So here, delta G is zero at critical point only. Otherwise, you have to put in some energy to get to the other side, right? If I were to go from here to here, this would cost some energy. So this would be delta G is greater than zero, right? And every point greater than that, say from here to here, delta G is less than zero, right? So any point past the critical point, anything that's on this line of two phases is going to immediately fall over to the one phase line. In fact, in reality, it doesn't even exist anymore. Okay, so what the idea is that you're kind of like, you can imagine that different phases, different orientation, you're just different, or it can be represented by different energy surfaces, and then there's this intersection point where the two surfaces meet. That's the critical point. And so if you have a ball rolling down this hill, and it's at this point, and it can either keep going or it can move over. And it just happens, entropically and enthalpically, it's always favorable to move over to the other side when there's just one phase. And so it just happens drama-free. But you still are changing the material. You still have a significant change because you're going from one energy surface that has some density and some heat capacity to one of a different density and heat capacity. Different behaviors. And so what that means, the densities are the same at this point, but the way that the density varies with temperature or pressure is different between these two. And so you're basically changing the state of the system in a drama-free way at this point. You still have to change the state. And so what I want to show you at the end is I want to show you two examples of this. Okay? One of the driving points of this is that this transition terms of equilibrium properties is drama-free, right? If the conditions are available, it can do it no matter what. It's perfectly allowed. There's no cost. So there's no cost to rearrange from two phases to one phase at CP, right? That's very different than freezing or boiling. There's a very, very dramatic enthalpic cost to go from liquid to gas or liquid to solid. There's an entropic cost, an enthalpic cost. You always have to put some energy or remove some energy. But here you don't have that anymore. The system can just transition smoothly from one state to another, no problems asked, right? It's got no problem. Right? And it doesn't have that barrier problem that we have either, that first order phase transitions have. It's completely drama-free. They're exactly the same energy. If you're at this point, you're just as equally likely to be at this point. And so they just merge together. So let me show you two examples of this. Right? So the conclusion of this, as I'm going to show you, is empirically, proving this is very, very hard. It wasn't until the late 1960s, early 1970s that a man named I can't get his name, Wilson, I can't think of his first name, won the Nobel Prize in the late 70s, proved that this effect of what I'm talking about is true for second order phase transitions and explain the mathematics of it, which are extremely complicated. But these are global phase transitions. What that means is that they occur everywhere simultaneously. There is no nucleation event. So I said they're drama-free. They smoothly vary. No nucleation, just happens. Look at two examples. All right, the first one I'm going to show you is one that's very similar to one you're going to do in the next rotation. This is a mixture of two molecules. This is a critical phase transition, slightly different than the critical point that we've been talking about. This is a slightly different one. This is a mixture of two liquids, two different organic materials. I can't remember what they are, but at some temperatures, they're two phases. They separate, like oil and water, different densities. And then at a certain temperature, they coalesce to a single phase. So it turns out that what's a binary mixture turning into a miscible mixture, a solvated mixture. That process of coalescence of two liquid phases into one liquid phase is also a critical transition that has the same physics and chemistry as the critical point of a supercritical gas and liquid fluid. So let's look at this video. This is going to start. This mixture is heated initially. So you can see it's one phase. It's in a hot bath. It's one phase. Very clear. Right? What he's going to do is he's going to pull it out of the hot bath and let it cool. And let's just watch what happens. This is a lot like that CO2 video, right? So the freezing, the freezing happens, but the critical point occurs. There's this murkiness, right? You have this one layer that's extremely murky. And then as the system moves past that critical point, it clarifies in two distinct liquid solutions, distinct liquid layers of different densities. Just a classic example of a two-phase coalescence. Right? The thing that I want to drive home, right, is that maybe it's not so obvious, but you can see that this did not happen in the same way that boiling or freezing does. In some sense, the entire system happened, transitioned immediately. The reason why it builds from the bottom to the top has to do with the fact that you have a temperature differential here. Here it's open to the atmosphere. So this surface is cooling faster than the liquid down here, right? Or there's some difference. In the temperature, there's a temperature gradient in here. So one part is cooler than the other. But you can see it happens all instantaneously. And as you hit that critical point, the whole thing goes murky. Now, why is it murky? Well, the reason why it's murky is because the density as a function of temperature, the derivative of the density with respect to temperature, is diverges at this point, meaning that tiny fluctuations in temperature lead to massive fluctuations in density. So what you have at this critical point is a liquid and a gas that are basically at the same enthalpy, right? But the densities, if there's a small differential in the temperature, some temperature gradient in this sample, the density that you see up here is different than you see down here as the temperature fluctuates. The average temperature is the same, but you might have a colder pocket and a hotter pocket here. And so you have these little pockets where you have a supercritical fluid with some density, and then might be another region that's just a tenth of a Kelvin colder, but because of the derivative of the density with respect to temperature is infinite, diverges, the density is dramatically different at that colder region. So now you can imagine that you have these crazy random temperature fluctuations moving across this entire test tube. And so what the system is doing as it moves across the critical point is simultaneously everything all at once, converting and rapidly fluctuating between gas and liquid. So you have these, not bubbles so much, but you just have these pockets that are averaged out that might be all gas, it might be all liquid, and they're interconverting wildly between each other, which causes it to become murky. We call this opalescence, what's called critical opalescence, because of course it happens at the critical point. It turns out that you have to take these samples up into space in microgravity. This is on a space shuttle in the 90s to show that in fact that this murkiness arises from the critical point, the density fluctuations that happen. And the reason why it's so murky is one is because the temperature gradient is large in your lab. The test tube is not a particularly good vessel for experiments. And two, we have gravity. And so if you think about, you have these dense pockets of liquid, some of them have influences of gravity more than others, depending on the density. And so the gravity actually plays a role. And so when you take these materials up to microgravity, to effectively gravity-free regions like the space shuttle, you don't have these problems anymore, and you get this beautiful. I wish I had a video of it. You don't get this murkiness much. You get this beautiful clarification, and you see the system constantly moving between two phases at the limit. Really, really cool. So so this is opalescence is indicative of the second order phase transition. It means that the density is divergent. In the same sense that when you boil something, the more you put heat into it, it doesn't heat up anymore. The more you fluctuate the temperature, the more rapidly the density changes at that point. It's the exact same behavior. Okay, in the last 10 minutes, I have one more example to show. I'm going to show you one more example of a second order phase transition. This is one that I think is really cool. So let me explain this very simply. This is what's called the Ising model. And it's a model of a two-dimensional magnet. The way this model works is very simple. All right. I'm just going to describe it to you. Imagine each one of these pixels is an atom. 256 by 256 in a lattice. Right? Each atom is 60 plates. And so think of crystal or solid lattice, two-dimensional, the plane of atoms. Each atom can be assigned, in this case, a color, white or black. And we equate these to in magnetism, we equate these to spin. Atoms can be spin up or they can be spin down. And the magnetism of the material is proportional to the asymmetry of the ups and downs. So if you have, or the whites and blacks. So if you have more white than black or more black than white, the material is magnetic. If it's 50-50, then the material is not magnetic. Right, so let me increase the temperature really high. Right. And here I'm going to plot what we call the magnetization as a function of time. Right, so what this does is it counts how many blacks and how many whites we have. You can see it's updating randomly. It looks much better on my screen. It's a little laggy on the Zoom. But this looks like TV static, okay? And the way that this is determined is basically we give each atom some energy, right? They have some heat confirmed by their temperature. And then we give them an interaction. Each atom can talk to each other's neighbors. What's the nearest neighbors? And basically, the way that we orient this is that if two neighbors are the same sign, right, so they're both white, we increase the energy by 1 unit. They're opposite, we decrease it by 1. Remember, negatives prefer to be away from positives. I think actually the way that does it is the opposite. I think the way this does it is that if you have two whites next to each other, the energy goes down by 1 unit. And if you have a black and white, the energy goes up by 1. So this is what's called an anti-ferromagnetic magnet. It doesn't matter. It's just an opposite. So what this is a magnet where lights like to be combined. Instead of lights repelling in opposite track, we have the opposite case. But the thing is that we've pumped in enough temperature in this system, and the interactions between the spins, the ups and downs, is significantly small enough compared to the temperature that the whole thing randomized. Right? This looks like a gas. Call this like a spin gas. Right? Everything is moving randomly, and you can see that this is the net magnetization, which again is just the asymmetry of white to black. It's randomly fluctuating, and it's on average 0. This is just a gas. Right? This is what iron looks like at room temperature. This is a great example of a sheet of iron. Each atom of iron has a little spin, and the spins have some heats, and they just flip back and forth. An iron in standard conditions, not magnetic. Now, what I can do is apply a field to it. I can apply a magnetic field to this and magnetize it. Right? If you take a piece of iron and you put it next to a magnet, it becomes magnetic. And eventually that iron stops being magnetic after a while, but you can charge up some magnetism in it. And so I can apply a field to it, right?
me turn the temperature down a bit so I can get it.
Right, and you can see now I have with my field, right, I've applied an external magnet to my metal piece. And so I have a positive field, so the system prefers to be white, which is positive. You can see there are more whites than blacks, and the magnetism of the material is 0.6, meaning it's magnetic. Okay, so I bring this piece of iron in next to a magnet, and the whole thing spontaneously magnetizes. Exactly how iron works. And the idea is that you just build this asymmetry of spins. So let me turn the field off again.
Right, and we go back to random.
When you put a piece of iron in front of a magnet, they do magnetize, and you get this kind of alignment of the arrows, spins, and colors, however you think about it. And then when you remove that magnet, the iron continues to stay magnetic, and it just decays slowly. It goes eventually, it equilibrates back to this. This is the end result after some amount of time. Right? And so what happens now if I continue to cool this? Right? What if I start pulling entropy out of the system such that the interaction between the spins, the like attraction, the opposite repulsion, become dominant? Right? What happens to the system when that becomes the dominant part of the energy, not the entropy?
So I could bring the temperature down to slightly above the temperature where
Something may happen. And let's look a little bit at, again, this looks like random crap. Right, you can see that the magnetism, again, is on average 0, but it fluctuates kind of slowly. Right? There are some parts where the system exhibits some positive magnetism, sometimes where it's negative, positive, negative, and you can see it has a wavelength, right? Some frequency, some period to that wave. It's a little chaotic. You can see there's some periods where it's up, and there's some periods where it's down, and then up again, and so on. Right? If I go back to a higher temperature, notice how much faster this fluctuates. If I go to 5, I double the temperature. That's a little hard to see, but after a while, we'll see that it fluctuates much more rapidly. It's going like this. Instead of going like this, it's going like this. You can kind of see that already. Right? So now I'm going to pull it right above the critical temperature for this system. Let's put it at 2.3. I think it's 2.3. Right. Now, what do we see? Well, we see that the blacks and the whites are starting to clump together. Right. And you can see that now that there, just randomly, there are more blacks than there are whites because there's a negative magnetism. But you can see the magnetism right there. It's trending downwards. It still has some fluctuation, but it's trending downwards. But what we're going to find if we wait long enough, I'm not going to sit here and wait for it. It will happen, though. Is that this fluctuation will flip. There will be some arrangement that will appear where there's more whites than there are blacks, and we get the same fluctuation, but it has a positive value. So this system is still fluctuating, but it's fluctuating much more slowly. Right? So it's going, instead of going like this, right, it's going like this. So what's happening as we get closer and closer to the critical point of this material, the wavelength or the fluctuation, the frequency at which the magnetism fluctuates, magnetism in some sense is very similar to the density of a liquid or gas. It's a very similar material property in terms of its mass. It's a second derivative of the energy. The fluctuations are getting larger and wider. And what happens when we hit the critical point? See right there, it just looked to positive, right? It's going to go positive and it's going to come back down again. If we wait long enough, it'll reach 0. There'll be enough times negative as it is positive. Now, if I bring it right to the bottom, right below the limit, restart. What we will find is that wavelength, that period of that wave diverges. Right? We saw that as we get closer and closer to the critical point, the period at which the magnetic dipole fluctuates from down to up, slows down. And in fact, what happens is, at the critical point, that period diverges. So basically, what happens is that you have an oscillation of your magnet at the critical point, But the frequency of that magnet, that oscillation is zero. The wavelength is infinite. And so what happens is that you get locked into a specific magnetic orientation. You're either on a peak or a trough of that wave, and it goes on forever. This happens simultaneously across the entire material. You can prove that at the critical point, the behavior of, say, this guy, this pixel, and these neighbors, right, a very local question, influences the results of all the ones over here. The entire system spontaneously reorganizes itself to become a magnet, right? This is a second order phase transition. Everything happens spontaneously and globally. And what happens is any randomness in one region influences the region of any other part. And so if you have some sort of condensation or magnetic formation here, some fluid formation, it affects the fluid formation and the magnetism all the way out on the other side of the system. So the whole system is correlated to itself and it transitions simultaneously together, unlike boiling and freezing. Boiling and freezing, this freezes and then eventually propagates out like this. But at a critical point, it all happens simultaneously. Okay? So that's the key difference between the two. All right, that's all I have for phase transition. Come back to chemical equilibrium on Monday. And we'll have new problems set for you guys on Monday as well. Have a good one.
Oh.
Yeah.
Okay, I'll be following you.
Okay.